So what I'm going to do is I'm actually structuring this today sort of in a format that you would do it yourself if you were laying things out. You know, we're talking about how to integrate faith and science in the classroom. So I'm just going to do it today. Like, you're going to be the students, just to kind of show you what that looks like. I've been a big fan for a while about integration, meaning how do you tie the two together while respecting the disciplines of each responsibly, because there is an irresponsible way to integrate. Don't use science to prove your faith. Hold your faith in confidence. So we'll talk about that stuff. But I just try to infuse, like we all do, the Eucharist is the source and summit of our Christian life. I just try to infuse everything I say with Christ. So we will go through that. The title, so this is actually what I wanted the title of my book to be. And I went around for a long time pouting because the publisher said nobody will understand it. And so I'm like, fine. And it took me like a whole week until someone pointed out to me, Stacy, particles rhymes with articles. Get it? Articles of faith, particles. And I'm like, oh, that's pretty cool. So I didn't even get the obvious. These thy atoms came to me in a moment of inspiration from my son. And the book, if you noticed, it's dedicated to JJ.
Is that him?
That's JJ. That's my youngest boy. He's now 8. He was 4. But when I was writing the book in my head, like I mostly wrote the book walking my German Shepherd in the Adirondack foothills, in the forest, literally. Like I'd get lost and my husband, I'd call him and he's like, you'll find your way home, honey, don't worry about it. And I'm like, thanks for that vote of confidence. And I would, but it was a good time just to sort of think, what is it that I need to say about this faith and science thing? Because I wanted to narrow it down just to one line that kind of captures everything I'm trying to get across. And I spent a lot of time thinking about it and writing the book in my head, and then I would go sit down and write it at night when I got back. But most of it happened while walking. There was one day when my husband had the girls out of the house, and it was just JJ and me. And I made him spaghetti and meatballs because that's his favorite. And I learned ever since my youngest daughter, Lucy, prayed the Our Father out loud and said, lead us not into the station. I realized that it's a good idea to have your kids pray alone because the youngest ones get drowned out when the kids all pray together, and sometimes you don't know what they think we mean by certain things in the prayers, like, where do you think we're going? But so with JJ, I'm like, JJ, I want you to say the prayer. Now, what had been going on during that time is I had started teaching chemistry online for Colby Academy in Napa, California from New York. And JJ was in my lap all the time, and he heard me teaching chemistry. He heard me talking about atoms with the great passion, which I have for atoms, because I just think they're the coolest thing ever. And he was getting his head around it, and he had been going through this long thing about, is my arm made of atoms? You know, he's looking and like, yeah, you are. Everything in your body is made up of atoms. There are atoms that make up the molecules, that make up the tissues, that make up the organs, and make up your body. And he's like, am I breathing atoms? Like, yes, you're breathing atoms, and God only knows where in the universe those molecules you just breathed in have been. Like, you don't know who else breathed them in, and you don't know where they were in the sky, and you don't even know what star they were made in. Like, they've been bumbling around this universe to get to your nose today. And so he just had this fascination. And there were other times, like he was throwing a ball in the living room and like, JJ, stop throwing the ball at the wall. I'm just smashing atoms, Mom. and he was just totally fascinated. I mean, the best was, and I wrote it in the book because it floored me. He came running by me, 4 years old. He's finally got the potty training thing down. He pushed me out of the way, running to the bathroom. Like, what are you doing? I'm going to pee atoms. And so he was getting his head around this pervasiveness of atoms. And so I said, JJ, why don't you say the prayer so I know that you know how to say it. I want to hear you say it out loud. And he said, in the name of the Father, and of the Son, and of the Holy Spirit, amen. Bless us, O Lord, and these thy atoms, he looked up at me like that, and these thy atoms, which we are about to receive from thy bounty, and he said the whole prayer, but he said, bless us, O Lord, and these thy atoms. And I'm like, that's it, out of the mouth of my son. That is what I'm trying to say about faith and science. You have to start with faith. We don't look at the table in front of us and say, I wonder if these mashed potatoes prove that God exists. I wonder if this lasagna is intelligently designed. I wonder if God just created that steak out of nothing and a miracle because I can't figure out how it possibly came from a cow. We don't do that. Like, we don't pick through nature in front of us and look for proofs of God. We start with gratitude. We look at the whole thing and we say, thank you, God, for all this. And that's exactly the way Catholic students need to be taught how to approach science. Come to science with gratitude and say, bless us, O Lord, and these thy atoms. Thank you, God, for all this creation. And then you roll up your sleeves and you go figure out how it works. And that right there changes everything. It reorients the whole dialogue because the students come to science with a reason to love it. When they're breaking their pencils trying to derive physics equations, all you have to do is say, that's God. God made it so difficult. God made it so ordered. You wouldn't be breaking your pencils if this were easy. And it inspires them. It also inoculates them. It inoculates students from ever being confused by atheist nonsense that we've been talking about. They never then have this approach to science where it either proves or disproves your faith. You just come to science saying, it's very liberating. You come to science, evolution, neuroscience, come to science saying, whatever scientists conclude, I'm just going to listen. I'm going to be open. I'm going to listen to what they're saying and accept it and help figure out what's right or wrong. I also talk about evangelizing through science. So once we get over the conflict myth and we're off defense, like constantly refuting atheists, once we take charge and get out in front and say, we're leading the way. Because the other part about seeing science in the light of faith is that we need people who practice virtue, who understand what true progress for humanity is when we get to bioethics. We need people out in the front leading the way for science. Because let me tell you, right now, a lot of people do things just because they can, and they're not asking whether they should or not. So how do you evangelize through science if you're talking to someone who's not a Catholic or who's not a Christian? You do it the same way you do it when you eat your food. If you're at a restaurant and you're there with an atheist, and we have been, we've had people come to dinner at our house who are not Christian, we said our prayer anyway. We're sitting there together with the atheist, and we say we're going to say our prayer and thank God for our food. And we thank God for our food. From that point forward, we're in communion with the atheist because we're all agreeing that the material world exists. We're all agreeing that there's order. We're all agreeing that the food is good. And so what it does is you just start from a different fundamental place. We say thank you for everything in science. The atheist doesn't. And I've been the atheist. And the atheist, frankly, hasn't got an answer for where all the order came from. Whereas we not only have an answer, we're saying thank you, let us now responsibly figure it out. And then you just go forward. And what you should do, because I work with Bishop Barron and the nuns and that the faith and science thing, what you can do from there is lead the atheist, go into science together, do all the science together completely. But at some point you might look at him or her and say, did you ever wonder where all this came from? So just be grateful and then do everything else with them. And it'll lead to good discussions. But that's what I want the students to do, is be confident in your faith. Pray the creed and mean it. And be confident. And I just want to, you teach with that. That's how you integrate it. You teach that way. I'm confident. I'm not worried about conclusions. If there's a difficult scientific conclusion that scientists make, if you know your faith and you know your science, you can pick through it. That's the course I'm teaching that when I met Chris. I was teaching seminarians how to pick through scientific papers. Because let me tell you something, theology teachers. If you can read St. Thomas, you can understand science. It's the same skill. And I just take seminarians and I show them how to do it. You need to look through what's in the scientific paper. I show them how they're structured, pick through what's consistent with our faith, what's neutral, and what's contradictory, and learn to just slice that part out and fix it up and put it all back together for people. And it's a good way. It's very intellectual. It's exciting. So I have JJ to thank for that. It actually led, the other reason, this is the first grade, First Communion Catechism, Baltimore Catechism, the very first thing we teach our children. God made me out of, JJ said, atoms. But what followed then with my first grader was a very fun little talk about the uncaused cause and creation out of nothing and secondary causes. Because that's another thing people get wrong all the time in the faith and science dialogue. He naturally got it. God made the atoms, JJ, out of nothing. He gets it. So we were all done with that. And then we just, but the thing is, you learn this. Okay, so I've handed out about thousands of these glasses now. I brought you something. You have to think like a scientist. I'm going to help you get there. Scientists use their imagination. Scientific models are pictures in our mind. Nobody really knows what an atom looks like. It doesn't look like anything. We have to imagine it. And then when you imagine it, and this is sort of why scientists tend to be nerds, you have to imagine how the atom looks, and you have to get comfortable putting things together. When I look at a tree, how robots, little things are clicking. Things are clicking in my head about the atoms. I will stand and look at a tree, and my husband's like, you're staring again. But you're thinking about the stuff that's going on, because it's clicking. So you have to get used to putting things together abstractly in your mind, and the mental pictures help you do that. If we didn't have mental pictures, but it doesn't mean when you see this that that's what an atom looks like. That is not what an atom looks like. But I can't draw it any better. So I want you to use your imagination. There's a box above all your heads. See it? Okay. You already have your chemistry glasses, don't you? There's a box above your head, and I want you to reach up. Go ahead. Nobody will think you're weird because we're all being nerds now. Open the box. There's a nice new pair of chemistry glasses for you, and I want you to take them out and put them on. So now we're going to shrink down into this realm that we call chemistry, into the atomville. You might notice that things start to get pixelated when we get down there, right? You look at something really close. Oh, it's pixelated. Yes. Things look different down at the atomic level. Things are pixelated down there. Now you're ready for quantum mechanics. It's not so difficult. I've spent my entire adult life thinking about evolving from atoms and particle wave duality. It no longer bothers me. It's like, I got it. Like my doctor said I was having trouble seeing. He's like, oh, we got monovision. You put one contact in to see up close, one contact to see far away. I'm like, oh yeah, I've been doing that kind of thing all my life. You just get used to it. It no longer troubles me anymore, okay? Because I have worked with atoms, thinking of the particles in them as particles and thinking of them as waves. It just depends on which set of equations you want to use. It depends on what you're trying to do. If you're trying to make lycra spandex like I did so pantyhose won't rip, you're thinking about them like particles. If you're trying to simulate photosynthesis to create alternative energy sources like I did in graduate school, you're thinking about it like waves. It's just whatever tool works, okay? And they both work fantastically. That's why I became a chemist, by the way. Stephen here? Okay, and our biologist isn't here yet? Okay, so don't tell him I said this. In physics, physics serves chemistry. You have to get all that physics down. We need those theoretical people, but if you're just theoretical, you just sort of sit and think. I wanted to make stuff. I wanted to do stuff. And so I didn't want to be a physicist because I wanted to actually make things, whether it was lycra spandex or Teflon or artificial photosynthesis to save the world. And biologists just memorize stuff. Biologists don't know why their things do what they do because they don't know chemistry. If you really want to know why biology happens, you have to know chemistry. So I was very specifically on a mission to be a chemist and not a biologist and not a physicist. I can do both, but that's because I like physics of chemistry. So So go chemistry. Chemistry is the central science. All right, now, in your atom world, so we're shrinking down into this crazy world that's pixelated. Imagine Penn State Beaver Stadium. It holds 110,000 people. In the middle of this stadium, and this is in chemistry textbooks, we do this with kids, but I don't think we spend enough time making them get the point. Imagine Beaver Stadium as big as it is. And notice, see all the people? You can't really see the individual people when you're at a distance, sort of morphs together, but they're pixelated too. If you got up close enough, you could see them. Imagine in that entire stadium, a little glass marble suspended in the very center of it. That's the atom. That's the nucleus where all the matter is, almost. And all that other space out there, when they say atoms are mostly empty space, that's where the electrons reign supreme. But most of the matter is in the marble in the center of this stadium. And this is very, very important. Okay, this is why atoms bond with each other, because they have this structure. This is why they hang together. This is why the universe hangs together. There's a very fine-tuned, precise structure to the atom, symmetry. In that marble are the protons and neutrons. The protons are particles that are positively charged because that's what we decided to call them. And the neutrons have no charge. Neutrons, you can think of them as being made of a proton and an electron. So that's why they're neutral, positive and negative, neutral. So the neutrons are just kind of like, they hold their mass. They just have mass. The protons are kind of what it's all about. The protons actually have mass as well. And I have a t-shirt that says, protons have mass? I didn't even know they were Catholic. That protons have mass. And I could tell you how we know that, but no, we don't weigh them on a scale. But protons have a mass that is very precise. It's 9.672, what is it? It's on the screen. 9.6726219 times 10 to the negative 24th grams. So that means, scientific notation, you got to divide by 10 a whole bunch of times. You cannot imagine a number this small, even down in Atomville, but let me try to get you there, okay? Think of a sugar cube. Nobody uses those anymore, but think of a sugar cube. Now, cut the sugar cube in half, okay? Got that in your mental chemistry glasses? You're picturing this? Cut the sugar cube in half. Now take that half of a sugar cube and cut it into 1 billion pieces. Got it? Now take one of those 1 billion pieces of that half of a sugar cube and cut it into 1 billion pieces. Got it? Now take that billionth of a billionth and cut it into 1 million pieces. Now you're down at the size of the proton. It is a millionth of a billionth of a billionth of a half of a sugar cube. That's negative 24 grams. That proton has this very precise mass, and it has a unit 1 charge, positive charge. The electron, does anybody know how much smaller the electron is? So now we got the proton. Is an electron the same size as the proton? No. The electron is 1/1846. It's almost 2,000 times smaller than the proton. That's why we say most of the mass is in the nucleus, because the neutrons are the mass of a proton and an electron. So neutrons and protons are almost the same mass. They just have that teeny little 2,000ths more. And they're all in the nucleus in that marble. The electrons are out here. There are calculations that show. So why is the electron the same magnitude of charge but opposite, but so much smaller in mass? We don't know. We just know that it is. And you also can do calculations. If in the beginning of time that electron had only been 500 times smaller and not 2,000 times smaller, it would have been so massive that as it orbited the nucleus, it would have crashed into it and atoms never would have formed, and we wouldn't even be talking about it right now. So the small size helps it keep in orbit. It stays in orbit because positive, negative. Okay, and that's how the atom's made up. But atoms don't have the same number of protons. That's what identifies each atom on the periodic table. Each element on here has a different number of atoms. Hydrogen has 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6. And you go on, all the natural elements, and then you have the ones we made from smashing them together to get more protons in the nucleus. Do you see any missing spots? Did God forget to make platinum with 78 protons? Did God forget to make ruthenium? There are no missing spots. There were at one time. But the world is so ordered that even those scientists said, leave the missing spot, because we're going to find an element that goes here. There can't just be a few missing here. They have properties. They're ordered for their properties. That right there ought to make every one of us get down on our knees and weep for joy and thank God for such an ordered universe. When your life gets really hard, think about the periodic table and tell yourself, God's got it. It's going to be okay. If He can hold all this together, whatever I'm suffering today is going to be. And people are usually the periodic table causes me suffering. Light then. So everything you're seeing right now is because of those blessed little electrons in the atom. Light comes from electrons, so they are pixelated. Electrons can't just hang out wherever they want to. They have to go in energy levels. How do we know that? It was observed. Specific energies, like we talked about yesterday, come out of the atoms and not in between. Okay, so there's a pixelation of energy at the atomic level. That's quantum mechanics. Quantum just means quantity. There's a specific amount. As the electrons jump, just think of floors in a building. As the electrons jump and relax, when they absorb energy like we were doing yesterday, they take that energy and they jump to a higher energy level. But when they lose that energy, is what we're going to talk about today, when they lose that energy and relax back down to a lower energy level, that energy, like Steve was explaining, has to go somewhere. That packet of energy, that precise difference in the energy of the higher energy level and the lower one, is what we call a photon. It is a particle of light, but it's a packet of energy. I have no problem with that. But that is light, everything you're seeing right now. Everything that comes to us from the stars, everything that comes to us from the sun, everything that is reflecting off all this. I wear black because just all the color, nothing reflects, and I don't have to worry about anything matching. It's hard to match clothes when you know about this stuff. Everything you're seeing is because of the electrons jumping around in the atoms. That is what light is, okay? Light and color. The color is the different energy levels, okay? That's it. That's everything you're seeing. See? Does that not change your life? Does that not change the way you look at things? Watch this. I'm going to play it a few times. There's an electron orbiting. Did you see it fall down, and did you see the packet? Right there, that's light. I'm going to play it again. Can everybody see it? This is a real important concept. The electron's in its energy level, n equals 3. It relaxes to n equal 2, and that precise amount of energy is given off. Yesterday, y'all were putting energy into the atom and exciting them. This is photo emission. And so scientists knew this. They don't notice you can't have half that energy packet come off. You can't. You can have multiples of it, but you can't have fractions of it from one energy level to the next. Now, in each atom, because of the different number of protons and the different number of electrons, every atom is precisely balanced uniquely. Okay, so not all energy levels are the same from atom to atom. Okay, it's like putting your kids in the room. The electrons don't want to be close to each other, so they're going to spread out as far as they can in different energy levels. And they're going to orbit around. And when two atoms bond, it's just because the outermost, the higher energy level electrons on one atom are attracted to the nucleus of another atom. And they're like, I'm going to go over here for a while. And when they're sharing electrons, we have a chemical bond. It was actually really, so the materialist mindset, when you think people are just collections of atoms and molecules because you don't believe in anything spiritual, that's what you have to conclude, that we're all just atoms and molecules. It makes your relationships very hard because you're like, don't take it personally, but I don't want to share electrons over there with you, and I'm going to do my own thing. And you just sort of have this mechanical, check the box. If I do this, my relationships will be okay. People have free will, atoms don't, and it's different. But it kind of is like overlapping orbitals when you, anyway, that's for another book. Let's just say it took a while, the body and soul thing, it took some thinking. But this is the language then. Orbits and energy levels are quantized. This is where Planck's constant comes in. Planck's constant, and we're not going to dwell on it too much, but I want it to make sense. Your students need these things to make sense. It's not just something to memorize in a textbook. Planck's constant was observed. It means that we can say the energy of these electrons is equal to the frequency. Frequency just means how many cycles per second. This is a low frequency. This is a low frequency. This is a higher frequency. No, this is higher energy. I get it mixed up. This is lower energy. It looks like lower energy. Energy and frequency are equal to each other if you multiply frequency by Planck's constant. Okay, so when they did experiments, they're like, this would equal this if we just multiplied by this. So that is a physical constant. It's something we observed in nature. It is called the quantum of electromagnetic action. See, that should make sense now. It's the energy carried by a photon at its frequency. Okay, it relates the energy carried by a photon at its frequency. Interestingly, in 2019, right now, I looked this up last night. I don't see it. Anyway, in 2019, so in physics, we have the base units, and then everything's derived from them. Since the 1800s, the kilogram has been defined by a mass sitting in France. And this is the international kilogram, and all grams are based on that. And it's protected, kept in a vacuum, weighed carefully, but they're literally, that's what we humans did. I mean, we're not, like God didn't say on a tablet on a mountain, this is what a kilogram is. We came up with that. We named a kilogram, we defined it, but what we're trying to do now is base our units on physical constants. And so now Planck's constant is actually used because of E equals mc squared. Energy and mass are related by the speed of light. Einstein. Because energy and mass are related by the speed of light, and Planck's constant relates energy and frequency, they now use Planck's constant to define the kilogram. So the kilogram is now based on a physical constant in the world. A second, by the way, is 9,192,631,770 oscillations of the two hyperfine splitting levels of the ground state electron in the cesium-133 atom. The time it took me to say that, somewhere an electron jiggled over 9 billion times in a cesium-133 atom that's kept. It gives out radiation, that's how they know. That's how precisely seconds are defined. Like when my kids were newborn and the day would pass, I knew how many jiggles in an electron happened in a cesium-133 atom somewhere because I figured it out. And my husband's like, why are you crying? I'm like, because time is passing and I'll never have a one-day-old baby again. But you're keenly aware of thinking of things that way. It's like sometimes I just can't converse with people because it's just going too fast. But it's neat to know that stuff, and that's what you want to inspire in your kids. Okay. So the photoelectric effect yesterday, I just want to point out, it's kind of like playing ping pong. I don't think teenagers today know what this is, but you guys do. It's kind of like playing ping pong. If you just stood here and your little packet of energy was just it just barely pulled it, we all know that little packet of energy you delivered wouldn't kick the ball up, right? It would just kind of rock there. And nothing would happen. That was what you were doing yesterday. You had to give it a packet of energy that was high enough to get the ball out of the atom, okay? Chemistry, so that's physics, but chemistry deals with what happens when the electron gets out of the atom. So then we tell it where to go. The fact that I'm doing this is shows that we have great control over electrons and atoms. Your cell phones are evidence that we have great control over these things because of chemists. But when it gets out here, so this is the same concept though. If you're irradiating atoms with small little punches, the electrons don't get enough energy to jump very far, okay? Now, they're always kind of jiggling anyway. That's what the hyperfine splitting states are. Everything's moving. The protons are spinning, these are spinning, and because of that, there's always jiggle. There's always energy. Nothing's ever still. But if you have enough energy, you can get the electron out. That is the photoelectric effect you did yesterday. What we're going to do today with the light flame test is the other way. So here, in photo emission, we are going to, so the electrons are in their energy levels, and they jump around on their own too. The electrons are in their energy levels. When you do the flame test and you put the salt, and we'll talk about it in a minute, into the flame, you add some energy and it causes the electrons to move. And when they relax, so they won't move enough to come out, it's when they relax, so they'll jump up and then they fall back down. When they fall back down, there is precise, it's like a paintbrush. When they fall back down, there's precise energies of relaxation that emit photons of precise wavelengths because they're precise energies, which means they're precise colors. Photons are being emitted all around us. We can only see what's in the visible region, okay? So that's what we're going to do today. This is the electromagnetic spectrum. This is all the wavelengths that we talk about when we talk about light. We can't see all the others. We can't see UV or X-rays. These are high energy. We can't see, this is heat, microwave. These are lower energy, longer wavelengths. So the frequency is increased over here. The wavelength is decreased. Just notice they go opposite each other. This little rainbow region here is the visible spectrum. We sometimes teach Roy G. Biv. Red is the lower energy, longer wavelength. Blue is the higher energy. When we do the flame test, you'll see colors because when those electrons and those metal atoms jump and relax, they're emitting very precise colors, okay? When you see fireworks on July 4th, it's because chemists figured out how to put certain metal salts into the firecrackers and make them go bang. That's where the colors come from in the fireworks. But all color, all light comes from electrons doing their thing. White light, like we see coming from the sun out there, white light has a continuous spectrum because there's so many electrons jiggling around. It's a combination, okay? It looks white. If you run it through a prism, it separates out. The high energy bends more, the low energy bends less. That's why it separates out. You can't, this is terrible drawing, and I'm sorry, it's imagination, but we all have our chemistry glasses on. We're down in this little tiny millionth of a billionth of a billionth of a half a sugar cube world. When you have a little tiny atom, and every element is different because it has a different number of protons, a different number of electrons, there's a different little balance in each little world. When you get down to the individual atoms, each atom has what we call a spectral fingerprint. The energy levels are slightly different because of the different number. One more proton changes everything. And so it changes the energy levels, which changes the emission spectrum. And so you have a different combinations of excitations and relaxations possible, and all that together gives a very precise light fingerprint coming out of an element. This is how come scientists know what elements are in the stars. This is how they know elements form in the stars. This is how they know the difference between white dwarfs and red giants and all of that. This is how we know the age of the universe, because the telescopes, this is one way we know the age of the universe. The light coming from the stars has been analyzed for many years, but we can see that the universe is expanding because, you know, there's a Doppler shift with sound. It's the same thing with light. And there's a red shift. And so they can measure how fast it's expanding and extrapolate from there the age of the universe. That's one way. There's another totally different way they estimate the age, and it comes out about the same. Okay, this is what we do with the pixelation. This is how we draw energy levels. This is the off-ball diagram. I just want you to see it today because these energy levels, these numbers just refer to n equals 1, 2, 3, 4. These are just energy levels, okay? N equals 2 is different for every element, but that's how we talk about it. In the first, this is just hydrogen. This is the first element on the periodic table. It's easy. Quantum mechanics started with hydrogen because it only has one electron. But look at it. With that one electron, it doesn't just sit in n equals 1. So we fill up the off-ball diagram because nature is disordered. It's like when you have more kids, I was saying you put them in different rooms. They start filling up, that you fill up one electron in each first, then you go back and pair them up, much to the chagrin of my daughters. They have to pair up. But they fill up very precisely. But the thing is, when you have just hydrogen and you have one proton in the nucleus, one electron out here, these are the possible transitions. So the one electron can jump from n equals 1 to n equals 2 and relax, 1 up to here and relax, 1 up to here and relax, 1 up to here and relax. Lyman discovered this series. You won't probably remember from the previous slide, I have other slides like that. These wavelengths are not visible. These are in the ultraviolet region. So these are not visible. The one electron can also jump here, it can jump here, it can jump here. These wavelengths are in the infrared region. Paschen discovered these series. This is just hydrogen. This is why quantum mechanics is so difficult mathematically, and they make you derive this stuff in college. The Balmer series happens to fall in the visible region. These are possible transitions of that one electron. Just imagine if you're trying to calculate this based on differential calculus, you're trying to calculate that for hydrogen, then somebody says, okay, do helium, you got 2 electrons. Imagine the possibilities. Quantum mechanics deals with all those possibilities for the higher level atoms. So they can't measure them all, but all the calculations are consistent with the observations, which is a good indicator to a scientist that you've got it right. So just appreciate that. Don't memorize it. Just appreciate it's like that when you look at the periodic table. I like this one because it shows these are different energy levels, but the 1, 2, 3, 4, 5, 6, 7 over there. So you've got 6 elements you're going to do today. And I want you to try to understand this based on what we're talking about. Each element has a fingerprint because of all the electrons, possible excitations and relaxations. You won't be able to get your head around what they actually are. Just know the more electrons, the more complicated it is. When an atom or ion, an ion is just an atom that lost an electron, is heated to high temperatures, electrons can be excited to higher energy levels. That's what you're going to do with the flame. Then they relax back. You'll see the light come out. A corresponding amount of energy is released with a particular wavelength and frequency. These jumps produce spectral lines of visible light. They produce ultraviolet. They produce light in other regions too, and there are spectroscopes that can measure all of that. That's one way of a chemical analysis. You can analyze the elements in something based on this because each element has such a precise fingerprint. So you're going to do some of that today. This is what hydrogen looks like. So instead of having the continuous rainbow, this is how they knew that matter is quantized and energy is quantized at the atomic level, because it looks like this. There are precise wavelengths and energies coming out of hydrogen, and they correspond to those wavelengths that were on that other slide. I put it all together here. This is so cool. Like, this is neat. This region right here that falls in the visible series, 656. Look where 656 is. This is 620, this is 750, 656 falls right there. So you can see this transition in a red line. You can see this transition, 486, it falls right here. That's what you see on a spectroscope. You are seeing quantum mechanics with your eyes when you do this test. You can do it with hydrogen gas. It just looks just like this. This is that third one, 434 and 410. So that is what hydrogen looks like because of its energy levels. That's how we know about quantum mechanics. It's not really mysterious at all. The particles are acting like waves. Big deal. It gives you a new appreciation for the periodic table. But when you get, so look here, I've got lithium. Here's lithium. Lithium has 3 protons. Lithium has 3 electrons. Oh, it's so much more complicated. 3 electrons. But what would you expect the spectral lines to look like compared to hydrogen? Would you expect to see more lines or fewer lines? More. And we do. And that's what lithium looks like. And so that pink color, it is like painting. The pink color is just all those colors mixed together from the spectral lines. That's the fingerprint. And that's lithium. Sodium, you're going to do, notice sodium is right here. So I picked these on purpose. Chemistry teachers do this when you, or if you wonder why they tell you what to do, this is one reason. So explain all this to your kids. Sodium is one more energy level down. So it's got electrons in the 3rd energy level, but you would expect the spectral emission fingerprint to be a little more complicated. Now what starts to happen, notice how the lines are getting fatter. What starts to happen is the transitions get so close to each other that there's just a whole bunch of little thin yellow lines and it looks like a thicker line. There's so many transitions close to each other. Potassium is the next one down, energy level 4. It's got more electrons. All those little arrows in the boxes are in how we draw the electrons. You can see what I just said. Isn't that cool? Like matter is so ordered. Every time you do it, bang, looks like that. That's how you know you have potassium. This is calcium. Calcium, notice, is on the 4th energy level, the 2nd row in. So it gets a little more complicated. And that's the color. That color that you see in the flame is the mixture of all those. Can you see? Strontium, and I've got some in here that are a little crazy. So what do you expect with strontium? Strontium is underneath calcium over in the 2nd row, 5th row, 2nd column. Notice how they're getting fatter. This is the explanation for it. So that's what we do in science. We observe. We just observe. That's what laws are. I've argued with so many scientists because they're wrong and I'm right here. Laws, theories never become laws. A law is something we observe. God did that. Okay, got it. Why did God do that? How does that work? That's what a theory is. Then a theory is when we try to explain what we see. And I've had people tell me, this is useful in the evolution debate, that evolutionary theory is a law. I'm like, evolution is both a law and a theory. You can see that it happens. You can see that there's changes. But it's also a theory when you're talking about all diversity of life. But theories themselves, so we're talking about 2 different things when you're talking about evolution, but theories themselves never become laws because we're just trying to come up with an explanation for what we see, and they're always different, okay? Theories can change. Copper, last one. Copper gets a little, there's an explanation for this we'll go through later, but this is what happens just when you think, your chemistry students get so mad here, just when you think you've got a nice pattern to what you're seeing, something doesn't quite look right. There's always an explanation for it. There's always, always, always an explanation. However, I can get chemistry students to the point where they're asking questions that nobody ever thought to ask before. Why does that do that? Nobody ever thought to ask it, and that's when you look at them and you say, you need to become a scientist. Because that's what scientists do. They ask questions that haven't been asked before, they come up with a theory to explain it, and they write a paper. So if they're thinking like that, if you're a Catholic, that is a great thing, because if you discover something new in nature, in creation, you have peered into God's creation for the first time and understood something for the first time that nobody ever, ever, ever has done before. It's a very wonderful feeling. I made nano bubble pack in graduate school, and I wasn't religious, but later I was like, thanks, God. So when you see the colors, you are seeing the direct consequence of electrons' excitations between energy levels. When I'm looking at your pink shirt, That's electrons.
You're not judging me.
I'm just saying. It's all the colors, okay? All the colors. Now, when those electrons, when that wave packet gets to your eyes and your brain does its thing, that's a whole nother story that goes on inside your head to interpret the light that hits your eyes. But that's where the light comes from. Okay, so now quickly I'm going to tell you the flame test, how to do it. What I want, when Dr. Baglow and Chris asked me to do this, I'm not real big. Like, this is one thing I don't like. When people come to chemistry lab, they're like, oh, we're going to blow stuff up. We're going to do crazy cool. We're going to pour things in beakers. I don't like that at all. I'm not very big on the show and show and show because I want you with your chemistry glasses on. I do. Parents have called me before. I taught for like 4 years at Colby Academy online, and I taught high school back in the 90s before I ever went to graduate school. So I've taught a little bit. Parents would call me and say, our son is staring at a glass of water. Like, I told him to do that. That's his experiment. Like, there's so much you can see going on at the atomic level when you're looking at light diffracting, when you're looking at bubbles forming, bubbles rising. There's so many things you can see. Think about what's dissolved in there, how water dissolves things. It's crazy. Why water is what it is crazy, is why we are alive. But I want that kind of wonder. I want you to look at everything with your chemistry glasses on. So this experiment's kind of simple, and it is, so honestly, it's fire because there has to be some kind of wow factor. Safety. We always talk about safety. So with high school, you have to do this. You guys are okay. I mean, we said don't wear sandals just because, when I worked for DuPont, I had to wear steel-toe boots, even though I was working with polymers. It's just a safety thing to be very careful. You really don't want to pour, like the bottle that says acid on it, don't pour that on your feet, okay? The stuff so if you don't want to wear goggles and an apron, it's okay. You don't have to wear the goggles. They are available if you would like to wear them. There's really not much danger in what we're doing today, but don't like stick it in your eye, because the salts will hurt. If you rub it on your clothes, it'll probably wash out. The sulfuric acid actually puts holes in your clothes, but we don't have sulfuric acid today. We have hydrochloric, and it really won't hurt your clothes. You can wear gloves if you want to. The salts are kind of icky. There's some rubber gloves over there too. Yeah, there's some rubber gloves. I do recommend pulling hair back when you're working with the flame. You're good. You're all good. See, you're ready to go. You should be the flame guy. Just, it's good to kind of keep it back because if you lean over, it's just like cooking. But it's nothing anymore. I mean, don't eat the chemicals. They'll be good. One of them, sodium chloride. That is just table salt, but I wouldn't eat it. But most people think when they come to a flame test, burn stuff, pretty colors. And that's how most chemistry programs advertise the lab. Burn stuff, pretty colors. No, you've got to get the kids to see what's going on in there. You've got to get them thinking about electrons jiggling around at the atomic level. It changes how they see it. And it goes on, so this is usually what kids, ooh, they're really cool. But a flame test is a qualitative analytic procedure used to detect certain metals based on each element's characteristic emission spectrum. See, I can read that sentence now, and the theology teachers hopefully know exactly what I'm talking about because we've talked about these words, right? Does that make sense now? It's precise language. It's just precision. Like I said, if you can read St. Thomas, you can do this. It's precision of words. Words are little packets. They have a meaning. They take it with them wherever they go if you're being logically consistent. If you're trying to manipulate people, you can make the words mean other things, like politics. But chemists and Catholics don't do that. A flame test is a qualitative analytic procedure used to detect certain metals based. They're both, like religion and science really are both the purest searches for truth. Everybody else, that's why, yeah. So anyway, the compound containing the metal is placed in the flame of a gas burner. Characteristic color is given off, visible to the naked eye. So there is some emissions going on that you can't see. You could if you had the right equipment, but your eyes can't see it. The color is caused by the heat from the flame, or so it seems. We get into a really interesting cause and effect analysis here. It's caused by the heat, but it's also caused by the heat making the electrons jump around. Fingerprint, these are used in fireworks. So I also picked this lab because I know July 4th is coming up. And I want to make sure you keep your chemistry glasses on when you go to the fireworks display. It will blow your mind. So what you're going to do, and after I finish talking here, we can take a break or get started. I'm going to give you time to do a number of things. And then I'll just talk again at the end of it. What's God got to do with it all? We're going to talk about that right at the end before lunch, okay? So what you're going to do, identify your beaker of water. It's the big one, okay? It's distilled water. Big one is water. The little one is dilute hydrochloric acid. If you need more, we've got more. Okay, thanks to the chemistry teacher. She makes those up for me. Label the white dishes and fill them with metal salts. So then you want to start and adjust the Bunsen burner. I'm going to show you how to do that in a minute. So we're going to start the Bunsen burner. You want to find the blue flame, the hottest part of the flame. I'll show you. You got to get the right amount of oxygen. It's a chemical reaction. You need to make sure the right reactants are going in. Then you have a nichrome loop at your desk. That's these things. So why nichrome? You can use popsicle sticks, but the popsicle sticks are made of atoms, and the electrons in the atoms of the popsicle sticks start jumping around too, and it messes up the color because it also gives off a color. So you want to just see the metal salt. The nichrome loop doesn't, I forget what it's made of exactly, but the electrons don't add to the color. So that's why we use it. So you'll have one of these. You're going to dip it in the hydrochloric acid to clean it. Metal salts become more soluble when they're in acid because there's more H+ ions floating around. They're kind of like, hey, rip apart, get away from each other, anion and cation, and they dissolve, and it helps to clean. Acids help clean salts because they make them more soluble. So the acid will clean your nichrome loop off between samples, because if you stick it in potassium and then you just say, I don't want to clean it, and you stick it in sodium, when you put it back in the fire, these spectroscopic elemental fingerprints are sensitive down to parts per million. So if you can't see anything on there, you think it's clean, it ain't clean. Clean it, or you'll mess up your analysis. When you're a chemist, it makes doing dishes really fun, because clean, it's atomically clean. My dishes are clean. Sometimes the glass gets etched, but I know how to get every last molecule off of my cookware. I also, it makes being Catholic interesting too, because I've asked priests this, at what point is the particle size, where's the threshold for the size of the particle size when the body and blood of Christ is no longer there? Because you say, you see them wiping off, and that's a pretty good way, but it's not complete. If your finger is not, how do you, yeah, where's the threshold? I ask them, is there a threshold limit of particle size? What nanometer range do we stop is it not? And the priest is like, just when you can't see it. I'm like, well, let's talk about what that means to see something. It's different. Also, dew does not fall. Dew does not fall. It's poetic, but dew doesn't fall. It wouldn't be as poetic to say when the water molecules condense out of air. But anyway. When you get it clean, then you want to place the loop in the flame. That also will help clean off everything. Dip the loop again. So between tests, you want to clean it with water, clean it with acid, clean it in the fire till there's no color coming out. Then you're ready to dip it into the next salt, okay? You can dip them into the salts either by dissolving the salts in a little water, but I don't recommend that. Just when the loop itself will just stick to the salts, and you'll see some on there, and that's okay. All right. And then clean it between each one, and then put it in the hottest part of the flame. All of these, 1, 2, and 3 are not good. 4 is what you want. So you're gonna mess around with the flame. When you get it going, you can turn the shaft, and that lets in more. It's just like a wood burner at your house. If you let in more oxygen, you wanna get it like that. If you have it flaming over there, you've got too much oxygen, and there's that actually glow is actually some soot starting to form, and the little black particles of soot, black body radiation, their electrons start jiggling around. You get this yellow. It's pretty if you're having wine in front of the fireplace, but we don't want it for our chemical analysis. So balance the oxygen to get the blue flame. That hottest part where the arrow is, you can barely see it, but that very tip of that inner blue flame is the hottest part of the flame. That's where you want to stick your nichrome wire. Do the compounds in this order. I will put this up here for you to see. The reason is that sodium, you don't want to do it last, but just go ahead and get sodium done out of the way because it's very bright. And copper chloride calcium takes a while to dissolve. Copper chloride tends not to clean off, so just do it last. That's just from experience. I want you to record what you see. You're going to have to answer one per group what you see. I'm not telling you what to look for. Record. This is what scientists do. Nobody tells us what we're supposed to observe. You're supposed to figure out what you're observing. Some of it you can see. So we have just little handheld spectroscopes, and if you look through it, you can actually see the lines. You can actually see the spectral lines that we're talking about. You can see quantum mechanics. I will put that back so you can see the order. The next thing I want you to do, so do all the salts, record what you see, okay? Be as descriptive as you want to be with the color. Because the truth is, you're not all going to name the color. This is part of science. It's an obvious point, but it's real. What I observe and how I describe it, you have to be very machine-like in how you describe things, because when you write a scientific paper, it's got to communicate to other people. It needs to be reproducible. And so that's where the technical language comes from. They're trying to be very precise in the communication about the scientific language. So think about how you would describe that color. The way chemists describe color is with numbers, with wavelengths and nanometers and energies, because that is precise. Magenta, I don't know what that even means. So magenta is a mixture of colors, which also has a number. That's why HTML code, you can do colors. After you do all those and write down what you see, the next thing you're going to do is get an unknown. I have unknowns here for each group 1 through 7, and in my super secret folder over there, I actually have what each of these are because I know what I put in here. And some of them are mixtures of 2 salts, some of them are not. And I know some of them you're going to look at, like you could tell by looking at it what it is. I tried not to use those in the unknowns. Like there's one that's blue. If I put it in there, you're like, duh. There are mixtures, some are mixtures, some are not, so you won't know whether you've got 1 or 2 things in there and you don't know what they are. So you try to figure it out, okay? Try to figure out what your unknown is. And then the last thing I want you to do is come up with a hypothesis. Based on your observations, predict what will happen when you mix 2 of the salts. Name the 2 you plan to mix. You can do 3. Knock yourself out. This is like cooking is chemistry. It's sort of like cooking. Mix them and then conduct flame tests. Record your observations. This is just one cycle of the scientific method. Comment on your hypothesis. Did what you expect to happen actually happen? So when you mix 2 salts, what do you expect to happen? Does it happen? What are the problems? Some of this, you're going to get a first-hand experience with how messy science can actually get, because as precise as this stuff is down at the atomic level, it's a little messy at the human level. And sometimes you're wrestling with nature and you're trying to make the atoms do what you want them to do, but it's hard. And I'll put these slides back up. Okay, so I've got some resources I'm going to share and then also talk about how to integrate all this. But you will have questions from students. So if you, in my experience anyway, if you buy a flame test, so a flame test is one of the least expensive experiments to do with high school students. It's one of the more memorable ones. And it is basically foolproof in that you will see colors with it. It's pretty hard for it not to work. It's frustrating with some experiments because they don't work, or they're expensive, or they require a lot of glassware. That's another reason I like the flame test. And it is, like I said, memorable. But you will get questions about why don't the anions show up? Why can't you use anything else? Like, why doesn't, a polymer or some other molecule? But it gets them to thinking about more of chemistry. Why don't the anions show up? Anybody? How would you answer that? Besides Google, which is how I answer everything. But why do you think the anions don't show up? So these were all chloride salts. The chloride is the anion. It's the negative. Chlorine gains an electron. It has a negative charge. It gets its electron from the metal. But why would you say, just based on what we talked about, why would the other part of the compound not show up?
It's not losing any electrons.
Or they're jiggling. They're always jiggling, but they're not jiggling. They're not giving, they're not in the visible realm. Or they're not getting enough energy they're just moving around, but they're not, like you said, they're not emitting any photon. There's no photo emission happening there. There's lots of different answers, but it all fits in with what we were talking about. Why can't you use some goo, why can't you use paint or toothpaste or something and put it in there? You can, and you might see a color, but it won't be pure. You won't know exactly what you're looking at. What happens so the reason we use metal salts is because those metals that we use, which were on the left side of the periodic table, potassium, strontium, calcium's a metal. The reason those show up is because they stay pure. They don't react with anything. Other compounds, other atoms, other types of atoms, other elements, they will, you can use a lot of them. Actually, I have. The reason we can't just use anything, though, is because it will start reacting in the fire itself. It'll start oxidizing, react with oxygen. And anytime you change the electronic structure around an atom, you learn this in organic chemistry when you get to college. You said you loved it. I hated that course. But when you get to organic chemistry, and you have these big macromolecules, which are lots of atoms sharing their electrons, one little extra electron can throw that whole system off. That's why we talk about free radicals aging us faster. It's because of an extra electron. And it is very much like, when get another kid in the house, it throws off the balance of everything. It's very much like that. All the other electrons are like, wait, we're all messed up now, and they have to reestablish a new equilibrium. But it changes the chemical properties of that molecule. It can make it more reactive. It can make it decompose. When I was designing lycra polymers for DuPont, that was one of the things we had to work on. We didn't want the polymer to decompose. We specifically designed one that was very durable in chlorine because chlorine tends to eat up polymers. The chlorine presence will react in certain places along the polymer chain, and it messes up the electrons and it breaks. You need lycra polymer to be durable in chlorine if you're putting them in Speedo swimsuits and selling them for $100. Because if the lycra in the swimsuit decomposes, you get that funny looking orange peel on the butt, that's not desirable. It looks like your swimsuit's degrading because it is. So those are things that you do with electrons. And I mean, what we have to do to get one of these to work is just phenomenal. The solid state devices, that's about controlling electrons. And when you touch your screen, a whole lot of control of electrons happens right there, especially if you're posting something to Instagram and shooting out to the whole world. There's a lot that has to happen for that to happen. But your students will ask questions, and there is an answer for the questions, but a lot of times I would ask the students to look up the answer for themselves, because that helps them learn how to use the internet for searching for things. But let me give you some resources. So chemistry teachers will know this one very well. This is ptable.com. It's a great, I like to use the orbitals. You notice I use some of that because you can see how, so look at these blue and yellow funky shapes over here. When we talk about energy levels and outer shells, I hate it when people say the outer shell of the atom, because it's not an outer shell. These shapes right here, look how crazy they get. So hydrogen is just a ball. Helium is a different ball. But when you get to these others down here, look at that shape. Y'all see the blue and yellow I'm talking about? That is the result of very complicated mathematics in 3 dimensions. It's the result of predicting the shapes of the orbitals. So the orbitals aren't just concentric circles. The orbital, only for the s orbitals they are. But for the other orbitals, their energy levels, so this is the 3-dimensional space in which we predict, based on mathematics and observation, the electrons spend most of their time. Although an electron could be infinitely far away, according to the mathematics. This is where we think they spend most of their time. As a chemist, that's good enough, because I can pretty much predict what that atom's going to do if I put it with some other atom. And that works, and I can control, I know, I call the periodic table God's Legos, and it is like playing with Legos in your head, but you've got to know the rules, because it's not just 2 dots and, snap them together. It is snapping them together, but you've got to know the rules. That language is what makes you a chemist. And it's fascinating. But these are what the orbitals actually look like. And when we talk about different energy levels, each orbital region has different energy. And so we're talking about jumping around. It's not just jumping between rings, but you see, we can't draw that every time we draw an atom. It works to think about them in rings, jumping up like floors in a building. P-table is good, though, because you can drive that point home to the students. Another one I like is, so just the Wikipedia for flame test. The Wikipedia article, I love Wikipedia. I donate to Wikipedia. Because it's really good with science. I'm trying to get it anyway. But it has explanations, but what it also has here, and this is where I got my pictures from, it has the colors. Some of you were asking about copper. Copper 2 is bluish green, copper 1 is bluish green, copper 2 is green, copper 2, and it's different between whether it's bonded with a halide or a non-halide. Halides are the chlorine, fluorine, bromine, this 7A over here. It's different. You don't have to know why, but every little thing changes the electronic energy, which changes the electromagnetic spectrum fingerprint for each element. But you can look and see, I only gave you 6, but there are colors for all of them. And I'm serious, when you see the fireworks, it's taking this knowledge and putting it into the package so that it blows up into a certain pattern, but the colors come from what you just saw. Another one is hyperphysics. How many of you physicists know that one? Hyperphysics, so it's an older website, and it's kind of clunky, but the information is really good. I can't make it any bigger. But this one is explaining, anyway, I'm not getting, there we go. This one explains some of the electronic transitions for sodium. Sodium, notice it had a very bright flame. It's got a lot of places for electrons to jump, basically. So you can see all that. And those are the main ones that I like. Okay, but back to, so let me get this down. Here we go. So this is basically what you should have seen. Did you guys all see that? Lithium was very pretty. Remember, its spectral lines were pure. They were pretty, there wasn't a lot of mixing the paint there. Sodium, very bright, almost white, because there's a lot of places for electron transitions. Potassium was almost white, but kind of pink. Calcium, strontium, almost indistinguishable, but not quite. But look, calcium and strontium are just one level apart from each other. So they would have some similarities in the copper-2 non-halide. Actually, that was a halide, yeah. But I think yours probably wasn't quite that green. I also said that was a ping pong machine, pinball machine, sorry. Thank you. Okay, so putting it all together now. This is a physics problem from the Principles of Physics online version from Kinetic Books, which was the book I used for my physics classes I taught. But this is not just a problem. This is how scientists deal with reality, okay? Science is about observing reality. It's all very Catholic. Observing reality and trying to figure out what the laws are that are repeatable and reliable, and then trying to come up with theories to explain them. And we ought to have great freedom in coming up with theories to explain things, because that's how, when you chemistry teachers teach the history of the atom, they used to think it looked like plum pudding. We are so far past that, but that happened in the last 100 years, less than that. So we didn't always know this stuff. In the history of mankind, that is a blip. So I collect physics textbooks, going back, the Resnick one, I think that's his name. I collect them because I have the textbook going all the way back to the first edition back in the 70s, and it's very different from the same edition, the same book, a new edition now. There's a lot more quantum mechanics in there than there used to be, because that has grown in my lifetime. That has changed so much, and it's hard to cram it all into a year even with students. But I always try to tie it back into, I mean, this stuff is happening right now. Like, you have atoms in your body doing this. This is not some abstract way off. It's just that you can't see that close into. But when we say God creates everything out of nothing and holds everything in existence, literally, God knows where all your electrons are in all your cells and all your atoms and molecules making up all your body right now. And we don't know even. There's so much science does not know. We do not know all the chemical reactions that have to happen just for your heart to beat one more time. The fact that you're sitting here breathing is not a miracle, because that's not what a miracle is, but it's amazing. And you don't take any moment, any instant for granted when you realize all this stuff is just going on. Like, sometimes you're just like, stop. I just wish everything would just stop so we could figure some things out, but things just keep going. And you can't. And that's what, when you're doing science and you're designing experiments, you have to deal with that fact that you can't make everything stop and study it. You have to work within the real world that you're given and try to figure out what's going on. Anyway, this problem is physics, but it's very much tied to chemistry. I tried to tie the disciplines together. A helium atom emits light of wavelength 471 nanometers. We know why. When an electron makes a transition from the n equals 4 state to the n equals 3 state. And you can't make up a problem like this and put in some number arbitrarily there, because that would be a not real problem. These are measured, okay? If the energy of the n equals 3 state, that just means the third energy level. is negative 6.04 electron volts. What is the energy of the n equals 4 state? So you can figure out problems like this. And students have to. But it changes what they're doing here. You know, this is just physics, but you have to put the energy in terms of joules. So you have to change it from, you have to use these units. And I have taken my students back with every single unit that's derived back to the fundamental unit and pointed out to them the kilogram is sitting in France, you know, or the second is based on jiggling electrons in the hyperfine state of the cesium-133 atom. You can take them all the way back to where do we even get these units from? Joule seconds, meters per second, meters based on the speed of light, how fast light travels. But you can take them through and notice the energy that you get down here. So first we're converting it to joules, then to electron volts, because that's how the question asks it. And then you just do a simple difference. This difference in the energy is the E final minus E initial. And you look at the electron states that it was jumping, and you've just got a simple math problem down here at the bottom, and you get that the energy in the initial state was negative 3.4 electron volts. So, but look at the answer you get, negative 3.4 electron volts. If you look on a table at the energy states of the hydrogen electron, that is one of them. I mean, this all has to fit together. But we're just fitting it together right now between chemistry and physics. But it does all make sense. It's part of the students. Kids these days want, I guess kids always wanted, things to make sense, to fit together, to be legitimate. They'll get excited about it if it's legitimate. I taught chemistry back in the 90s in Athens, Texas. Before I went to graduate school, I taught for 2 years, and I was not religious then. And I know firsthand, when the kids in your class say, why do I have to, I mean, it's very difficult. So many adults hate chemistry because of what I'm about to say. You have kids in the classroom, and they want to know, why do I have to memorize all this stuff? It's hard. I don't get it. I don't see what the point is. And if you don't have faith in God, you just kind of have to say, because it's required to graduate, because your parents made you, because the school makes you, the state makes you, because you need it to get into college. You don't really have a good answer. I mean, you can say that's how the world works, but it still falls flat. Kids are not interested in how the world works at that level. They're more interested in the latest iPhone or how many likes they got on Instagram, or, you know, they're more interested in other things. When you have a kid who's been raised in the faith, you can say, because this is how God created the world. Even if you don't become a scientist, to know this for this year, to look at what's going on around you at this level with your chemistry glasses on, you have those chemistry glasses forever now. You will never not know this, and you can appreciate it, even if you don't become a scientist. A lot of my students did become scientists. They went on to study science in college for that reason, because they understand it had meaning for them. And I'm on a mission. The only reason I started talking about faith and science was to evangelize. You're escorting them up a mountain. You're walking with them up this mountain of knowledge. And I personally experienced this. I wrote about it in Particles of Faith. It's like I climbed this mountain of knowledge in chemistry, and I got to the top of it, and I looked off over the cliff, and I knew there was so much more. And I just turned around, and I didn't want to look out there and deal with it. But if you have an atheist and you can escort them through all this knowledge, which is why we should not be the conflict myth defending all that, we need to jump into science, walk with them through the knowledge. At some point, the obvious question is, if you're a scientist, you're supposed to say why? At some point, you have that big why. Why is it all here? And science won't be able to answer it for you. And you either keep following truth wherever it leads you, which is what a good scientist does, or you turn around and ignore it. I mean, I had those epiphanies, especially when I was trying to simulate photosynthesis, looking at trees. And I literally turned my back on a tree once because I did not want to think about what was going on there. And I converted 15 years later, but I never forgot that. So, you know, I think there's also that, and then also with atheists, you've got to not just do the intellectual part. You have to show them that you won't drop dead if you lead a life of faith. You know, you just got to be a joyful, living the life of faith. I know it's a very simple concept in evangelization, but it speaks volumes. When I was ready to convert, that was a powerful thing, that I knew people who could live the life of faith, and I wanted what they had. And I had the confidence that maybe I would be okay if I did that too. So they need to see that you can. I think it's good to be, but I do have students like you're talking about. I teach a class at Seton Hall University called The Theology of Science, where I talk about the theology of science. I just turned it around. What theological attitude you need to have for science to really make sense. And I get atheists in my class. I also get Catholic students who are in their senior year of college and they're science majors at a Catholic college, and they still ask me, "You mean there's no conflict?" And I get it all the time, but I have atheists in that class because at the Catholic college they're required to take a Catholic studies course, and they challenge me, but I just try to answer their questions, and yeah, it's difficult. It's always going to be there. The course I teach, Theology of Science, based on Father Stanley Yockey's work, and we go through all the ancient cultures and how pantheism stifled a love of systematic order in nature. And we go through them specifically, and I have students from those cultures, and so I have to handle it very delicately, and I don't ever say, oh, Christians were the only ones who could come up with science. I show how the other cultures all contributed it, because they were searching for God and they were searching for truth, and how we took, just like St. Thomas Aquinas did, took what the Greeks had and purified it, picked out the parts that weren't consistent with our faith, but kept everything that possibly could be kept. It's like combing tangles out of the hair. And we just need to do that. I don't think enough people do that today in our time. I don't think enough Catholics, because evangelization is my thing now. I'm working for Bishop Joseph Strickland. I don't think enough Catholics are confident enough to dive into all the secular stuff, parenting books, psychology, neuroscience, evolution, politics, whatever it is, confident enough that you can pick out, like I taught the seminarians how to do with science, pick out what's not consistent with our faith, keep what's good. I read lots of parenting books now, and I do that all the time because there's a lot of tools for dealing with teenage girls and anxiety, got a few, that we don't get when you're just studying religion. There's a lot of stuff about how to help those girls deal with living the modern life, and a lot of it's very Catholic when you look at it, and then you get to the chapters that aren't, and you have to be able to say why they're not good. But anyway, yeah, today evangelizing, you don't get any shortcuts. You have to know your faith, and you have to know that other subject too. We have to do twice the homework. So emission spectroscopy, back to this. It works for about 70 of the elements. When you get to the bigger ones, it's just too crazy. There's too many, you just get white. There's too much paint in the bucket. It works though in the parts per million to parts per billion range. This is a simple, reliable tool for determining how much of impurities can be in water, like when they're testing the levels of salts in water. You can use this. It's qualitative, but it can be made quantitative by comparing it with standards. Rapid, convenient, selective can be performed on gases or dissolved or solids like y'all did. The atomization is done by a flame. It's one of the most common types of elemental analysis. You don't just get you have atomic absorption, so that's when energy is absorbed. There's also fingerprints about what different elements will absorb. There's fingerprints about what they give off. There's fingerprints about what happens when they give fluorescent spectra. Sometimes they absorb energy and it causes light to come out that's not due to the energy transition here, but it's some other combination of transitions. But there's all kinds of photoluminescence that goes on. You know, fireflies do it. Fish in the sea. Molecular spectra are complicated because when you're just dealing with atoms, everybody's keeping to him or herself. But when you put them together, like in Catholic teaching, when I learned about the sacrament of holy matrimony, I was like, I know this. I know what we're talking about here. When you put two together, you can't get too close because the nuclei are both positive and they don't want to be, but the electrons are bonding them together, but then it changes everything. It's like when two become one, yeah, everything's different. But that happens in nature. Astronomical spectroscopy, just so you know, there's a priest's name at the bottom, the Secchi classes, came up with this this is some of the data they use to look at stars. Elements form in the stars. Hydrogen has one proton, and in most stars there's just hydrogen burning, like our sun. Hydrogen, the nuclei are fusing, so that's what happens. The nucleus, where the protons are, fuse. If two hydrogens fuse, you get the second element on the periodic table, helium. Helium is a noble gas. It's very stable. In the stars, helium will hang around for a while instead of going back to two hydrogens. It will stay helium for a while. Because it does, a helium can nuclear synthesis, so the nuclei bond, not the electrons. Helium and another hydrogen can make lithium. But helium still hangs around too. It doesn't go back to two hydrogens. Two heliums can come together and make beryllium. A beryllium and a helium can get together and make carbon, as in carbon life forms. So carbon, which has 6, can synthesize with another helium because it's still hanging around and make oxygen. And it says in the Pearson AP chemistry textbook, I found it, I look for language like this all the time. It says when it's talking about this, it says that the origin of all the elements is in the stars. No, not origin. That's where they're made. And it says, but not all elements are created equally. And what they mean by that is that some elements are made in more abundance than others. And it says right there in the secular textbook, it says, scientists have no idea why there is a curiously high abundance. That's what the word they use. There's a curiously high abundance of the elements necessary for life on Earth. In the universe, there's a curiously high abundance of carbon and oxygen and hydrogen. And there's a longer story about how we think life came to be on Earth, but it just keeps going, the logic about how we're all here and how we're all connected in very precise ways at the atomic level. So what do flame tests have to do with God? There's a periodic table. It's just little things like that. Hang that beneath your periodic table. Can you see what it says at the bottom? It's another wisdom quote. But thou hast ordered all things in measure and number and weight. Wisdom 11:21. If you look for it, my first book is called Science Was Born of Christianity, and it's Father Yockey's work, and I teach from that book in that class at Seton Hall. But if you look for it in the liturgy, like when you're doing the readings and in the hymns that we sing, this view of nature as creation, praising God for his handiwork, this very scientific view, is pervasive. It's all through the Old Testament. In the beginning, God created everything out of nothing. Genesis 1:1, in the beginning God created. John 1:1, in the beginning was the Word, rationality, order. We as Catholics expect to find order in the universe. And there it is right there on the periodic table. If there weren't order, you wouldn't be able to have this table of God's Legos and make stuff like cell phones. I love my cell phone. There's another way I like to put it, and we were talking about this with C.S. Lewis the other day. This is from Frank Sheed, who's one of my favorite apologists. He's awesome, street corner apologist. The way he writes is beautiful. He doesn't waste a word. Like read his writing sometimes, none of his words are wasted, but he tells this story about seeing everything in the context to which it belongs. And he talks about, I tell the story my own way, but if you have, it works with young people. I've told it to a lot of young people, a lot of groups. If there's a guy who has a crush on a girl, and the guy says to the girl, I really think you're beautiful. I think you have the most beautiful eyes I've ever seen. And the girl's kind of a scientific nerd and takes everything very literally. If the girl said, gee, I want to find a way to give him a gift and thank him for his affections and show him I like him too, if she plucked her eyeballs out of her head and put them on a plate, everybody's thinking of St. Lucie now, and she put them on a plate and she handed it and said, here, I want you to have my eyeballs because you think they're so beautiful. That's not what he meant. He meant that her eyeballs were beautiful in the living context to which they belong. And Frank Sheed says, it's the book Theology and Sanity. He says he's not talking about sanctity, which is of the will. He's talking about the intellect and sanity, that you have to see everything in the context to which it belongs. When we look out at the universe, we are seeing the universe in the context of God the Creator. And if you were to take eyeballs in a lab, say that you were born and raised in a lab and you never went out into the world and you never saw another person or a mirror, but you spent all your days dissecting eyeballs and you knew all about eyeballs and how they work down to the atomic level. You knew all about eyeballs from dissecting them in the lab. You wouldn't really know what an eyeball is. You might know all about it, but if you had never seen an eyeball in a face, you wouldn't really know what it is. You can't sunder things from their living context. And it's the same with science and faith. I say science without faith is like eyeballs without a face. Because if you're just doing science, and I speak from experience, if you're just doing science, you put yourself in a prison of your own making. You intellectually chain yourself from asking bigger questions. And science will not be able to answer all your questions. When I became Catholic and understood the birth of science and how the scientific revolution happened in the Christian West for a reason, because of a theological worldview, and I understood that science is the study of the handiwork of God, it made me love science more. It made me realize that my love for science had probably been a search for God all along. And so it wasn't like, how can you be Catholic and have faith and still be a scientist? And like, I've never seen an electron either, and I can make those things do just about what I want them to. You live that way with mystery, like we were talking about. But I love to put it that way to students. You have to always see science in the context of faith. It doesn't really make sense if you take the faith part away. It is like just looking at an eyeball. Oh, here's the science textbook. This came out of the Brown LeMay. Some of you may use this book. Chemistry, the Central Science, told you. 13th edition. This was the Pearson AP textbook, one of them. Notice right there they say, the lightest elements, hydrogen and helium, along with the very small amounts of lithium and beryllium, were formed as the universe expanded in the moments following the Big Bang. All the heavier elements owe their existence. This is where you pick out things like, that was sloppy. Owe their existence to nuclear reactions that occur in stars. The heavier elements are not all created equally. So I show that to atheists sometimes. Like, we all know things are created. Like, don't we? Doesn't that just make sense to say created? Like, an atheist will use the word created. It's like, wait, hold it. What do you mean by that? You know somebody did this, right? God. But this, I thought it was funny that language was there. This is more, and it talks about helium, carbon, and oxygen being the most abundant, the elements for life. This is more than an academic curiosity, given the fact that these elements, together with hydrogen, are the most important elements for life on Earth. So I just look for things like that to point out to students. But switching over now more to biology, because that's what we're going to get into next. We have these labs working together. And notice chemistry's on Wednesday because it's after physics and before biology. Switching over, this what we were talking about, I know I'm so arrogant about chemistry. What we're talking about with electrons, though, is so fundamental to our life and to our existence. I mean, it's light, we're talking about light. God created light. It's coming from those atoms. But this is a picture of, who knows what this is a picture of? Biologist? Photosynthesis. Right. It's the light reactions of photosynthesis. And this was part of what I was trying to simulate in graduate school, just doing one electron jump. In photosynthesis, photons come from the sun. So they stream down, take 8 minutes to travel to the sun, travel from the sun here. They hit leaves out there. On the leaves, on an average tree, in every square millimeter, we can imagine that, there's 500,000 or so chloroplasts, very abundant on the leaves. These chloroplasts have inside them lots of things, but they have these little thylakoids, a pancake stack thing. In the membrane of that pancake stack, the thylakoid membrane, where there's 500,000 or so chloroplasts on every square millimeter on a leaf, are these nanomachines that do this. When the photons stream down from the sun and they hit these reaction centers are so structured in that membrane of the thylakoid that they are just the right angstrom scale spacing apart, so that when the photon hits a chlorophyll molecule, which is that big thing over there, that cyclic tetrapyrrole with the magnesium in the middle. The magnesium is one of these salts like y'all were using today that has an extra electron going, I want out of here, like a teenager about to graduate high school. I want out of here. And when that photon of light hits it, it absorbs the energy and the electron leaves the chlorophyll molecule. We see green on the leaves right now because all the other colors are being absorbed. Green is being reflected. All the other colors are being used. That energy from the sun, these chlorophyll molecules also have chemical variants with slight chemical differences such that they absorb all the colors of the visible spectrum, except green. And when that electron gets excited, it enters this dual system of photosynthetic pathways. These are the light reactions. In that thylakoid membrane, the electron jumps to a plastoquinone, and then it jumps to a bound plastoquinone, then it jumps to a pool of plastoquinone molecules. That's what the Q pool is. But it doesn't go back. So it's being handed down like a hot potato. It's being passed. And the energy at each little step is very precise. And then it gets to the plastoquinone pool, and it becomes a plastoquinol, which reduces the cytochrome B6F complex, which pumps protons into the thylakoid membrane, and the electron then goes to another photooxidized pigment molecule in photosystem 1. It gets excited, and it goes through yet a number of these ferredoxin, and they're just the right spacing and electrochemistry such that the electron gets passed again. I worked for 4 years to get the electron to jump one time, which is why I got so mad at the trees when I was a graduate student who didn't believe in God. And that's just the light reactions. Meanwhile, that photooxidized chlorophyll molecule, remember we took its electron away? It's kind of got a hole in it now. That's when water comes along in the environment, and it gets its electrons ripped off of it because it's like, I need another electron. And it takes it from the water, and that's where the oxygen comes from that we breathe. Meanwhile, we're exhaling carbon dioxide, and there's the pancake things, there's the membrane, see it's all perfectly ordered. And then you get over to the light, over here where it says CO2 fixation. The air we're breathing out, the carbon dioxide coming out of us, is used by photosynthesis and in the light independent reaction. So we're not talking about photons coming from the sun, we're all done with that now. In yet a whole nother set of cycles, the Krebs cycle, I remember memorizing those. I don't have them memorized now. I have the light cycle memorized though. But when it gets over there, that energy that was generated from changing nicotinamide adenine dinucleotide phosphate into NADH plus and adenine ADP and ATP from ADP, adenine triphosphate from adenine diphosphate in a phosphate donor group. When all of those produce the energy that when you get to the light independent reactions, the carbon dioxide is made chemically, synthesized like a factory into this 3-carbon precursor, which goes on to make all the parts of the tree. The starches, cellulose, the leaves, the fruits, the trunk. And then what happens? Animals eat it. When we eat an orange, you literally are eating energy from the sun. When you eat a fruit. And then it goes into our bodies. I was trying to simulate photosynthesis in graduate school as an alternative energy source. Non-believer though I was trying to copy God a little bit and simulate it because photosynthesis globally uses 6 times more energy from the sun than the entire human population. And the leaves just flap out there, you know, doing their thing.
Blocking it.
Trees. And so, but it's just doing that. And who was the physicist, Richard Feynman, once said that trees are basically made out of air because all the photosynthetic process, the end game is to take light energy from the sun and turn it into biomass, carbon biomass that fixes the carbon dioxide. But I go one step further. If you think about it, all the biomass on Earth, and if you look in the biology books where life first came from, there was no oxygen just floating around our atmosphere in the beginning of our planet. Photosynthesis had to happen and generate this stuff, oxygen. All the biomass on Earth, so all of that energy that photosynthesis around the globe takes in, 6 times more than the human population, it uses some, I put it together once, quintillion, that's 10 to the 18 kilojoules of energy, and it makes 100 billion tons of biomass. So all the living things start with photosynthesis. And that energy, you know, you just change, when you eat fruit, you take the energy that the fruit was made from, that trapped it from the sun, and then your body uses the energy, and then, or if you eat a cow, you're using the energy the cow got from the grass, which did the same thing. But all the biomass is made that way. And it's fascinating. Welcome to my world. That little piece is what you were just looking at with photosynthesis. This is all the biological molecules that come from photosynthesis. They all do. DNA's on there, RNA's on there, proteins, amino acids, all of it. And this is all put into one chart. These are the major metabolic pathways in living things. And it blows your mind. How can you not believe in God? And this all happens because of the periodic table. How can you, so I just tied chemistry to biology. I started with physics. How can you not believe in God and look at this? The only way I could do it was just to ignore it. And that when I turned my back on it, this was the book I was looking at when I had that moment. I was trying to figure out how to get one electron to transfer and stay put. And I looked at a tree and I was like, I'm never going to graduate. And that's what I did though. All I cared about was this layer of reality. I wanted to graduate. The tree be damned. I just wanted to graduate, and I knew I was never going to be able to get there. But when I decided to accept faith, granted intellectual assent to the truths of faith, it just opened my eyes up to a much bigger reality. I didn't have anything to fear. But now that makes sense. And I'm not kidding you. What I want students to do too, I can take a walk and look at trees and break down and cry. I mean, it is very moving when you look around at what happens. This is my youngest daughter, Lucy, named after St. Lucy. When you just walk out in nature sometimes and you think about all that stuff I just told you, you think about where light even comes from and the fact that your child is breathing and living and with you, it changes the way you appreciate the gift of a day. It changes everything, and you live your life with much more purpose. This is one of those wisdom quotes. It's just Wisdom 7:17 through 21, if you want to write it down. But it's very scientific. It's that scientific thing I'm talking about. For he hath given me the true knowledge of the things that are real, things that are. To know the disposition of the whole world and the virtues, meaning the power of the elements, the beginning and ending and midst of the times, the alterations of their courses and the changes of seasons, the revolutions of the year and the dispositions of the stars, the natures of living creatures, and I have a German Shepherd. I know all about the natures of creatures, and rage of wild beasts, the force of winds. Wind is all chemistry. And reasonings of men. I haven't figured that one out yet. The diversities of plants and the virtues of roots, and all things as are hid and not foreseen. I have learned, for wisdom, which is the worker of all things, taught me. That's what it means to be a scientist. And I love this quote from Pope Francis. So one of the things I tell students, see science in the light of faith. And I got it from Lumen Fide, the light of faith. Those are two of my two more daughters. That one turned 13 and that one's 15 now. But they've been raised this way, like JJ. Students were taught this way. It's infused in everything. That's the integration. Everything. By stimulating wonder before the profound mystery of creation, faith broadens the horizons of reason to shed greater light on the world, which discloses itself to scientific investigation. That's the way to view science. So I try to, in this day of Twitter and Instagram, I try to leave just one-liners. Like JJ said, these thy atoms. You know, we still pray it that way at the Trasancos household. But see science in the light of faith, which means you have to be confident in your faith first. Science is the study of the handiwork of God. That's it right there. That is the definition of science. Science is the study of nature. Nature is creation. Science is the study of creation. Creation is the handiwork of God. If you teach a kid that, they will never be confused. The conflict myths will go away in the next generation if all the kids who believe in God start thinking this way. And pray the creed and mean it. It's right there. Somebody said it yesterday. It's right there when we pray the creed. I believe in God the Father Almighty, creator, hello, of heaven and earth, all things visible and invisible. That's all you got to say. So a lot of it with students and integrating faith and science is just giving them permission to say things like that. It's okay to say it, you know, and challenge your friends who are atheists. Escort them up that hill of knowledge and help them if they want to turn around.